If you were to open up your data sheets right now, this is what you'd see on the first page inside your little data booklets. Where are we going to find the charge of the electron and the proton on here? There's stuff all over the place, right? And a lot of this stuff we don't even going to recognize, right? Units, right? SI units, the prefix is an atto, what? A pico, a femto? What's a positron or an alpha particle? Where are we going to find what we're looking for here, the charge of an electron? Exactly, right over here, minus 1e. But what does that e mean? Brad? Good, it's what we call the elementary charge, and you'll learn more about the elementary charge in our 4th unit. Basically, it is the smallest possible charge you can have, and its value is 1.6 times 10 to the minus 19 coulombs. So the charge of an electron is minus 1e, or minus 1 times the elementary charge. So the charge of an electron would be minus 1.60 times 10 to the minus 19 coulombs. Similarly, the charge of a proton would be plus 1.60 times 10 to the minus 19. An alpha particle, hey, you haven't even learned what an alpha particle is yet, and you won't for quite a while, actually. But we could determine what the charge of the alpha particle is pretty easily right now, right? 2 times the elementary charge, or it would be 3.2 times 10 to the minus 19. You're going to use the charge of an electron a lot in this unit and throughout the rest of the year. Okay? We'll probably just remember the charge of the electron because we use it so often. But in the event that we don't, we've got to be able to find it on our data sheet. And I don't want you come, June, 2 weeks before our diploma exam saying, yeah, you know what, I can't find the charge of the electron anywhere on my data sheet. Okay, it's right here and it's right here. You got to combine those two. All right. A couple days ago, we introduced two terms, conductors and insulators. And a conductor, you can see on the board right now, is a material in which the electrons in the outermost regions are free to move about, at least relatively free to move about. The materials that have the electrons more free to move about are better conductors than the ones that are less free to move about. An insulator, exactly the opposite, right? The electrons on their outer levels aren't so free to move about. Give me a good example of a conductor. Not the general category, but a specific example. Good. Copper's a good conductor. Give me another one. Gold is a very good conductor. Good. Aluminum is a good conductor. So basically we're talking about, in general, metals, right? And an insulator, okay, a material that doesn't conduct electricity that well, a material that doesn't have its outer electrons free to move about. Give me a good example of an insulator. Rubber is a great insulator. Air is a good insulator. Wood is a good insulator. Good. Basically, we're talking about non-metals, right? 3 laws of electric charge. Nothing new here, right? This is grade 9 stuff. Third one's a little bit tricky. Talk about that one in a little bit more detail. But first 2, opposite charges attract each other, right? We talked yesterday about a lot of times opposite people kind of attract each other. If you're too much alike, you don't get along. Okay, you're too much alike, you kind of repel each other sometimes. You kind of butt heads if you're too much alike. Okay, opposite charges attract just like opposite people attract. Like charges repel each other or they push away from each other. And then finally, this is the one that is a little bit trickier because we have to have this objects thing in there. Charged objects attract neutral objects. Now, why does that happen? Now we know why this happens. Rucker? Would a neutral atom also be attracted? I would have to say no, Rucker. I'd have to say no on that one. Let's draw a picture of what actually happens here. I drew this picture yesterday. We got a neutral object with 2 positives, 2 negatives, or 16,000 positives and 16,000 negatives. It doesn't really matter. We bring a negatively charged object nearby. That's a neutral object. That's a negative object. Charged objects will attract neutral objects. Why? Why does that negatively charged object attract that neutral ball there? Brad? Good. So the positive, we'll stop right there for a second, Brad. So the positives in this neutral object stay where they are. The protons can't go anywhere, right? They're in the nucleus, and unless the nucleus itself can go somewhere, then these positives aren't going to go anywhere. But the negatives do. The negatives are affected dramatically by that negatively charged object. Where do they go, Brad? Good. They're going to be pushed away to the opposite side. Now, we still have a neutral object, but we have what's called a, starts with an S, three words, separation of charge. We've got a separation of charge here where the left side is negative and the right side is positive. Lo and behold, this side right here, the side that's closest to the charging object, is oppositely charged. That's why this charged object attracts this neutral object, because the side that's closest is opposite. It's really because opposites attract, right? Opposites attract. That's why charged objects attract neutral objects. Okay, what's the overall process for this called, by the way? We talked about that yesterday. It's a separation of charge, right? And it's temporary because when I take this away, it goes back to the way it was. What's the umbrella term for that, though? Induction, right. If you remember yesterday, guys, we said induction is a way of charging objects, but it never involves a transfer of charge, and it never involves the two objects touching each other. Okay, this doesn't involve touching. This doesn't involve a transfer. All we're doing is creating a separation of charge here. And that's why the charged object attracts the neutral object. While we're on that, while we have that diagram up there, how would we make that permanent? How would we make it permanent, Janessa? Yeah, put a ground wire on. So I put a ground wire on. What happens there, Janessa? Good. So those two electrons that were pushed to the far side are now going to be pushed down into the ground. Now, that leaves us with a positive object. Not a separation of charge, but a positively charged object. But if I take this charging object away, they're going to come right back up there. So how do I make it permanent, Wilson? We're close, right? We're close. Yeah. Good. We're going to cut the ground wire. Hey, let's try this. Let's take that away. Let's put the ground wire over here. Does that make any difference? Interesting question here. I got a negatively charged object, bring it nearby on the same side as the ground wire. The negatives get pushed over to the left-hand side. Now they can't go into the ground, right? Does that make a difference? Would it affect it, Katie? So you're saying the electrons now might not go down into the ground, Rucker? Sorry, 1 sec, Rucker, just 1 sec. Because they went to the other side? Okay. So is it possible that maybe electrons could come up here because they're attracted to the positive over here? Rucker? Who says the negatives are going to go to the left-hand side here, and we're not going to get the same effect as we got when the ground wire was on the left-hand side? Okay. Who agrees with Rucker here and says the negatives will still find a way to get into the ground, and it's going to end up with the same effect as it was before? Okay. Slightly more people saying that. Yeah, they're still going to find a way. They're still going to find a way. These electrons that were just pushed to the left-hand side a minute ago, they don't get pushed to the left-hand side per se. They get pushed as far away from the charging object, from this guy over here, as they can. So when they get pushed as far away as they can, they were right here, right? They were scattered throughout. When they get pushed as far away as they can is not the left-hand side now. As far away as they can is down here. So they're going to be pushed not over here. They're going to be pushed down here and into the ground. So we get the exact same effect. It doesn't matter where you touch it with the ground wire. We get the exact same effect. Does that make sense? All right. While we're on that, let's draw another picture here. Once again, we got a neutral object, but this time we're going to bring a positively charged object nearby. What happens to the protons in there? Tyler, what happens to the protons in that neutral object? Nothing. Good. They're going to stay where they are. And what happens to the electrons in there? Good. Assuming we don't have a ground wire in there that's, on the left side or the right side, whatever, they're going to move towards the object. Good. So let's draw them over here. Now we've got this separation of charge where the left side is positive, the right side is negative. Right side oppositely charged to the charging object, so it's going to attract. Charged objects attract neutral objects because of this temporary separation of charge. I want to try something a little bit different, though. Instead of attaching physically, literally, a ground wire and sending it down into the earth, I just want to bring this big, massive something nearby it and actually touch it. So I don't know what this thing is. Maybe it's a big globe. Maybe like a big desk globe. I don't know what it is. It doesn't really matter. In the end, it's made up of protons and electrons just the same as this other neutral object is, right? What's going to happen here? Which way? From the blue one to the red one, or the red one to the red? From the red to the blue? Yep, they're going to be attracted to the positive object. Good. So we get a bunch of electrons in there. Now, if we take this guy away, the charging object away, then those electrons are going to go probably back where they came from, right? But if I cut that connection or pull it away a little bit, then those electrons can't go back where they came from. What have we just done? What have we just done? Okay. But what's the term I'm looking for here? Yes, yeah. I grounded it. Right? It's the exact same thing as grounding it. Instead of attaching a ground wire to this big object that we call the Earth, we brought the big object, whether it's the Earth or some other big object that can provide extra electrons, just touched it directly. It's the exact same thing. The exact same thing. So if you ever get a question like that where you're touching this big object that can provide extra electrons or be a sink for electrons, then it's the same thing as grounding. Hey, don't look at that and say, oh, that's, it's not, you may not have the picture of the ground wire, but it's still the big Earth or whatever that's touching, just directly this time, touching the neutral object. Make sense? All right. It's charging by induction. We also talked about charging by conduction. Remember, induction never involves a transfer of charge, and it never involves touching. Conduction always involves a transfer of charge, and it always involves, or usually I should say, involves touching. What were the two subcategories of conduction? If you don't remember them, think about them. Think. Sometimes we're better off doing that, actually, not memorizing what the two are, but we're better off visualizing. Okay, what did we do to charge two objects by touching or by transferring? Hayden, what's one of them? Good. Charging by friction. Rub the two objects together. Rub the balloon against your hair. Rub fur against a piece of plastic. Rub your comb against the hair, or whatever the case may be, right? Charging by friction. Kinetic energy liberates the electrons from one material, and they flow to the other material. What's the other way of charging by conduction? Sometimes we just call it, sometimes we just call it conduction. But sometimes we call it contact, charging by contact. Now, the ironic thing about this is that the one that's called charging by contact doesn't actually have to involve contact. Give me an example of a situation where you can charge by contact or by conduction, where there isn't actually physical contact being made. Yeah, good. A little static shock arc. If you touch somebody and you see that that shock happens just before you actually make physical contact. Or you walk over to the light switch. Sometimes you walk across the carpet, you touch the light switch, you get shocked. If it happens just before you touch the light switch, that's still charging by contact, but you're not actually physically making contact. Sometimes, if it's a dark room, sometimes you can actually see it. You can actually see, like, basically a little mini lightning bolt being formed, right? You're talking probably somewhere in the range of 15 or 20,000 volts there. All right, One last thing, and then we'll, one last thing for review here at least. We talked about the law of conservation of charge, which says, same as the law of conservation of anything else, right? Blank can't be created and it can't be destroyed. It can be transferred, but that's about it. Let's do one quick example with that, and then we'll move on to some new stuff here. Let's say we've got 3 charges here. First charge is 5 coulombs. The second charge is minus 3 coulombs. The third charge is plus 10 coulombs. We're going to touch charge 1 and 3. Then we're going to touch 2 and 3. And then we're going to touch 1 and 2. So we got to figure out what the charge on all of these things becomes by the law of conservation of charge, by charging by contact. So we start off with 3 objects, 1, 2, and 3. We start off as 5 minus 3 and plus 10. What's the total charge there, by the way? 5 plus minus 3 plus 10 is 12. We'll just put that off to the side, and we'll make sure in every step that we do here that we keep a charge of plus 12 coulombs. All right, 1 touches 3. 5 touches the 10. So 5 and 10 makes 15. What are they going to balance out to be? Good, 7.5 and 7.5. Is it possible to have 7.5 coulombs? Sure it is. They don't have to be whole numbers. A coulomb is a gigantic unit of charge. Therefore, it's easy to have a half of a coulomb. Right? We can have a tiny, tiny fraction of a coulomb since it takes 10 to the 19 electrons to make a coulomb of charge. 2, by the way, remains minus 3. Add those up, we get 12 coulombs. So far, so good. 2 touches 3. Minus 3 and 7.5. Minus 3 plus 7.5 is 4.5. Divide that by 2, it gives me 2.25. This one remains 7.5. Add those up, and once again, we get 12. So far, so good. Finally, 1 and 2 touch each other, 7.5 and 2.25. That gives me 9.75. 4.875, 4.875, and the last one's going to be 2.25. If we add those up, 4.875, 4.875, 2.25, we end up getting 12. So what's the final charge on all 3 of these? 4.875 coulombs, 4.875 coulombs, 2.25 coulombs. Make sense? Got an example of an application that we see out there in life that uses these principles of charging by induction and conduction and electrons and protons and so on. This is what we call an electrostatic air precipitator. What it does is essentially filters out pollutants, dust and pollutants from the air electrostatically. Most times when we have in our furnace at home, we have a filter in our furnace, but it's a mechanical filter most times. That mechanical filter is literally, it's some fabrics and weaved together that basically doesn't allow small particles to go through. So it allows air to go through, but it doesn't allow small particles to go through. It mechanically filters out dust and dirt and whatever, so the air ends up being cleaner. You're supposed to change them every 3 months. If you look at your furnace filter after 3 months, or you leave it a little bit longer, 5, 6 months, that thing is filthy. It's filthy. And it's filthy because the air in your house is largely filthy. Okay? And as it goes through the furnace, that sucks out or filters out some of that dirt. This is an electrostatic air precipitator, which works even better at sucking the dirt out of it. Here's how it works. We've got a battery down here, or it's not really going to be a battery. It's going to be just some kind of power supply, probably plugged into the wall, right? With a negative end and a positive end. And that negative end charges these blue rods negative. I don't know if you can see that from where you are or not, but they're labeled as negative. From up here, you can see it. These blue rods are charged negative, but it also charges these red plates positive. Now, air goes through first, it's blown through in between these blue negative rods. And this air contains pollutants, contains dust and whatever else. What happens as the air rubs up against these negatively charged rods? Neutral air with dust particles rubs up against these negatively charged rods. What do the dust particles become? When neutral touches negative, they have to become negative and negative, right? Just the same as when we were charging by contact here yesterday. Touch something that's 0 and plus 5 together, they become 2.5 and 2.5. Something that's 0 and negative 5, negative 2.5 and negative 2.5. When you touch something that's neutral and negative, they both become negative. How much negative? Well, we don't know. We don't have any numbers here. But neutral and negative have to become negative and negative. So these dust particles now become negatively charged. These little dust particles that were labeled as green here are now labeled as blue, indicating that they've become negatively charged. Still there, still got the air going through, still got the dust particles as part of the air, but now these dust particles are negatively charged. What happens to these negatively charged dust particles now as they go through these positively charged plates? They get attracted to the positively charged plates. So they stick to the positively charged plates, and then, of course, the air just keeps going through. So what happens on the other side? What do you have? Well, pretty clean air, because the dust particles were electrostatically removed, not mechanically removed. So you're not limited by the size, right? When you're talking about a mechanical means of separation, you're limited by size. If you have a particle that's small enough, it might fit through the filter. But in the electrostatic precipitator, it doesn't really matter what the size is, right? Because it's electrostatically attracted to the positive plate and removed that way. Get to the other side, and you've got relatively clean air, right? With as much of these pollutants removed as possible. This is not a curriculum objective, by the way. Okay, so don't worry about copying this diagram down. This is an example that illustrates our curriculum objectives of charging by induction, charging by conduction, right? Got another one for you. We're painting a fence here. This is my backyard, by the way. Maybe not. There's an ocean, I guess, in the back. Not quite my backyard. I wish it was my backyard. We want to paint this fence, but we don't want to take the fence down, and we don't want to do it by hand because it doesn't do a nice, even, smooth job when you do it by hand, and plus it takes a while when you're doing it by hand. So we want to spray it. But we want to be careful because we don't want to have to cover up all the cement in my, on my deck beside my pool. Okay, I don't want to get black paint all over the grass and so on and so on and so on. So what do? Well, we painted electrostatically. We have this electrostatic painting gun that has this rod inside it. And that rod might be charged negative or positive. We'll make it negative. Doesn't really matter. As the paint goes past this negatively charged rod, the neutral paint goes past this negatively charged rod, what happens? When the neutral paint touches the negatively charged rod, what happens? Katie? It gets negative charged. So now the paint is negatively charged. These paint droplets, these paint tiny little particles are negatively charged. If it was a positive rod, they'd become positive, right? Okay. So now we get these paint droplets that are negatively charged. This metal fence, this only works if you have a metal. Okay. If it's wood, it doesn't work. This metal fence is touching the ground. It's grounded, right? Now that metal fence wants to attract this grounded metal fence wants to attract these negatively charged paint drops. So as you're spraying it, what happens is that the paint droplets go like this. Okay? Some of them are going to go towards it anyways and touch it and coat it anyways. But even the ones that go past it, as opposed to going over here and getting the patio or the pool itself all covered with paint, the ones that go past it tend to be attracted back like this to the back side of it. So there's two purposes here. One, you have less waste of paint. You have very little overspray of paint. So you don't wreck your your deck or your pool or the grass around it or whatever, most of the paint actually goes to the metal. The second thing is, you can almost paint it from one side because you get coverage in the back by spraying it from the front, right? All the overspray from the paint goes around and coats the back. Does that make sense? So in both cases, this case and this case, we had some charging by conduction. Right? When the paint droplets were going past a negatively charged rod, touched it, charged negative, that was charging by conduction. In both cases, this case and this case, we also had charging by induction. The charged objects were attracted to the neutral objects. Does that make sense? So both cases, we had a little bit of both. A little bit of charging by conduction, a little bit of charging by induction. I got two multiple choice questions. I'd like you to take your phones and submit both of these as multiple choice number 1 and 2, please. So submit them both together as 1 and 2. 37 and 38 in your booklet. Question number 37. Most of you said for number 37A, but there was still about 30% of you that said something different. It says, the bottom of the thundercloud usually becomes negatively charged. Before lightning strikes, the charge of the ground directly beneath the thundercloud will become what? Well, forget about the tree for a second. Okay, the lightning bolt, forget about the lightning bolt. We got a thundercloud up here that's got positives up here, and we got negatives right here. That's a separation of charge, right? This cloud is probably neutral, but through rubbing together of water droplets, whatever, the bottom of the cloud has become negative, the top has become positive, a separation of charge. Now, the lightning is about to strike. Essentially, we're looking at a negatively charged cloud right here, right? Because the part that's closest to the ground is negatively charged. Here's the ground. The ground is effectively neutral with an equal number of positives and negatives. What's going to happen to the protons in the ground as a result of these negatives in the cloud? What's going to happen to those protons? Protons aren't going to move. What's going to happen to the electrons? They're going to be driven away. They're going to be pushed away, down deeper into the earth. So the part of the earth that's closest to the cloud, the part of the earth directly beneath the cloud, is going to become positive. Positive by what? Positive by induction, positive by conduction. Has charge been transferred? Has the cloud touched the earth? Nope. So what's it called? Hayden? It would be positive by induction. The answer is A. 38. During the downward strike, the charge on the top of the tree becomes what? Well, if we're not told whether the lightning bolt includes negative charges or positive charges, but we know since it's coming from the bottom of the cloud, and the bottom of the cloud is negative, then the lightning bolt is going to be a bunch of electrons being transferred down. So, what's the top of the tree going to become as these negative electrons are coming down there? Yeah, it's going to become negative, and it's called conduction because these electrons are being transferred down. It's not physically touching, right, the cloud and the tree, but charge is still being transferred. So negative by conduction, the answer is B, which is what most of you said, but still about 30-something% of you said options C and D. Let's just take a look at those. Neutral by induction. Okay, we know it's not induction, right? We know it's not induction because the charge is being transferred. Okay, that has to be conduction. Neutral by conduction, well, if negatives are being transferred, okay, then it's going to become negative. If you receive negatives, you're going to become negative. Yep. I'm sorry? Oh, I see. Yeah, I guess, yeah. That would happen ridiculously quick, right? During the lightning strike, for the duration of the lightning strike, it would definitely become negative. There would be so much negative charge coming down from the cloud, it would definitely become negative. One more question here, guys, and then you can work on some check and reflect questions. I'll have you guys work on this one again and submit this one, please, as multiple choice number 1. Got a range of answers here for this one. Most of us have picked one particular answer, though B. We'll see if that's right. It says a student places a positively charged sphere near the end of a metal rod. Both are in insulated stands and the rod is grounded. Why the insulated stands? Why are they telling us this? Why does it matter that this positively charged sphere is insulated from the ground? Right. If this was attached to the ground, then electrons would be transferred up from the ground to it. Now, even if they didn't tell us it was an insulated stand, we probably wouldn't have even thought of that, right? The electrons being transferred up that way. Okay? But it could have happened. So they're just saying, look, if you're one of those people that are just thinking of all the different possibilities, don't worry about that. The electrons aren't going to be transferred up through the ground here. The only things that we have to worry about are this, and then the connection with the ground right there. All right. What's going to happen? What's going to happen to the charges on the rod? Well, this positively charged object is going to do what to the protons in this rod? John, what's going to happen to the protons in this rod? Nothing. Protons stay where they are, always, right? Unless you have a hydrogen atom is one proton. And hydrogen would be a gas normally, right? So in that sense, a proton could be moved, okay? But normally in the case of a solid, certainly, and atoms other than hydrogen, protons can't move. So protons are going to stay where they are. What's going to happen, Aiden, to the electrons? They're going to move towards X. So the electrons are going to be pulled over as close as they can from there. In fact, not only are they going to be pulled over from Y, but they're going to be pulled up from the ground as well. Right? That makes sense? So what's going to happen? Well, and X is definitely going to become negatively charged, right? Definitely negatively charged because they're pulled over from Y and from the ground. And that's going to happen because electrons are moving onto the rod from the ground as opposed to onto the ground from the rod. That makes sense? What would we call that, by the way? Charging by induction or conduction? Induction? Yes. Now, some of you are thinking, wait a second. He said induction never involves a transfer of charge. And there's kind of a transfer of charge taking place there, right? Electrons are going up from the ground to there. Isn't that conduction? Listen very, very carefully here. This process we still call induction because the thing that's doing the charging right here isn't transferring charge and it isn't touching. It's still induction. Now, there is conduction taking place within that process, right? Electrons are moving from the ground to the object. But the overall process, again, we still call induction because the thing that's doing it isn't transferring charge. Make sense? All right, here's what I'd like you to work on for the rest of class, guys. Page 523, questions 6 to 10. Actually, let's go 523, 7 to 10.